energy density in electric fields. Okay, so that means what is the energy present per unit volume, that is the energy density. Okay, so energy and work done, they are one and the same, right? So whenever you have a system of charges, okay, so let us take Q1, Q2 and Q3. There are three charges, let us say. Okay, so the energy that is associated with this system is nothing but the work that is done to assemble the charges. Okay, so that means if you take, let us say this is P1, P2 and P3. Okay, the point name we have taken as P1, P2 and P3. Okay, so first let us bring Q1 to point P1. Okay, so at this point of time there is neither Q2 nor Q3. Okay, so then what will be the work done? The work done is 0. Okay, since there is no other charge, present, the work done to bring it is 0. That means simply there is no work that is done. Okay, now what we will do? Bring Q2. Bring charge Q2 to point P2. Okay, then what will be the work done? The work done will be against the force that is exerted due to Q1. So work is to be done against the force exerted due to Q1 on Q2. Okay, so it can be a repulsive or an attractive force depending on whether they are like or unlike charges, right? Now next what you can do, you can bring the charge Q3, then finally bring Q3 to point P3. Okay, so now what will happen? Work is to be done against the two forces exerted, one due to Q1 and the other due to Q2. Each of them are going to exert a force on Q3. So we have to work against two forces. Okay, so work is to be done against two forces, one due to Q1 and other due to Q2. Okay, so we don't need to go into the mathematical derivations of this. We can write the final expression here. You're going to get the final expression for the work done will be 1 by 2 Q1 V1 plus Q2 V2 plus Q3 V3. Okay, so what are V1, V2, V3 here? They are the potentials at P1, P2 and P3. Potentials at P1, P2, P3 in the presence of all three charges. In the presence of all three charges. Okay, so this is the final work done. So here we have taken only three charges. Okay, just for the sake of understanding, we can take n charges. Okay, in general, if there are n charges, then what will be this is work done is nothing but the energy, right? So we will represent this as WE. Okay, the electrostatic energy associated with the system. So this is going to be 1 by 2 summation of 1 to n charges qk vk. Okay. So this is in general for system of n charges. So the charges can be positive or negative. Okay. So here we have taken the case of point charges. Okay. More general will be if you can take an electric field, right? So because of different various charge distributions, you're going to get different electric field expressions. Okay. So we can write in terms of electric field. Okay. So if electric field is given or it is known, then the electrostatic energy is given as electrostatic energy WE. This is given by 1 by 2 integral d bar dot E bar dV. This is a volume integral. Okay. So we know that d bar and E bar, they will be in the same direction, right? So d bar is equal to epsilon E bar. So you can write 1 by 2 integral epsilon E square dV. So here you can see that it is no more a vector, but it is just a magnitude, because we have written the expression for the dot product, right? Dot product we are removing, so we don't have to consider about the vector, only the magnitude is enough. Okay. Now from here you can get the energy density, right? So energy density is the energy per unit volume, right? So that is nothing but differentiate the electrostatic energy with respect to volume. So this expression you have to differentiate. So just integral whatever is present, you are differentiating it, so you will get the expression that is present inside the integral. Okay. So and into the constant as well. So you are going to get the energy density is equal to half epsilon E square. Okay. You can write in terms of the electric flux density also, d square by 2 epsilon. Okay. So this is the energy density. Remember here E and D are magnitudes only. We don't have to consider the vectors. Okay. Because energy is associated potential also, right? Potential does not have any direction. It is not a vector. It is a scalar quantity. So similarly, energy density, which is nothing but the work done, right? Energy and work done are one and the same. So energy density also we are concerned only with the magnitude. There is no need for any vector.